You look up at the night sky, teeming with billions of stars, each one a potential sun for untold planets. It feels like common sense, and frankly, a lot of our science tells us we absolutely should not be alone in this immense universe.
Right. It seems almost mathematically inevitable, doesn't it?
Exactly. Yeah. And yet, where's everyone? Today, we're diving headfirst into what many consider the universe's most profound and perhaps most uncomfortable secret. The Fermi Paradox.
That's right. This isn't just about speculating on little green men or, fantastical sci-fi scenarios.
No flying saucers today.
So, probably not in the way we usually think. Our deep dive today is really a journey through some of the most ingenious and sometimes pretty unsettling explanations scientists are currently grappling with.
For why we haven't found alien life.
Exactly. For why they're so hard to find. We've pulled together some fascinating sources for you, and we'll try to extract the crucial insights, helping you understand the uncomfortable truths that might be hiding behind this cosmic silence.
And, as you'll soon discover, these truths are profoundly thought-provoking. We're going to explore a really fascinating range of theories.
Yeah, from the idea that maybe Earth is incredibly special, incredibly rare.
Which is kind of a lonely thought.
It is. Or, on the other hand, the unsettling possibility that advanced civilizations might just not make it. They don't survive themselves.
Or maybe they're even deliberately hiding from us.
That's on the table, too. It's a cosmic mystery with very real implications for us, right here, right now.
Definitely. So, let's begin. Where do we start with this enormous question? Okay, let's unpack this. The whole thing started not with some, grand scientific paper or a dedicated research project, but almost casually. Over lunch.
Yeah, you got to picture this. It's 1950, just 5 years after World War II ended. We're at Los Alamos, the legendary lab in New Mexico.
Where they developed the atomic bomb. So big brains, big ideas.
Exactly. Intense atmosphere. You've got Enrico Fermi, Nobel laureate, one of the key figures of the nuclear age, just chatting with colleagues. Imagine the kind of conversations they had there, right? Yeah. The intellectual energy.
Boundless possibility seemed to be the theme.
Totally. And the conversation apparently drifted towards some recent UFO cartoons, the kind you'd see in the New Yorker. I think one involved aliens stealing trash cans in New York, believe it or not.
Seriously? Trash cans?
Yeah, so they were talking about, the feasibility, maybe just the absurdity of alien visitations. And then Fermi, with this, disarming simplicity.
He just drops the question.
He just asks, almost as an aside, so where is everybody? Just like that. And that simple, almost off-the-cuff question, boom, it became the seed for one of the deepest paradoxes in science.
Wow. So why did that question stick? Why did it become such a big deal?
What's truly fascinating here is why it blossomed into this full-blown paradox that still bugs us today. It's all about scale and probability.
The sheer size of everything.
Exactly. Consider the vastness.
Yeah.
Our Milky Way galaxy alone, just one galaxy out of billions, has over 200 billion stars, maybe more.
Mind-boggling numbers.
Right. Now let's try applying some incredibly conservative estimates, like super cautious guesses.
Okay.
Let's say just 0.1% of these stars are sun-like, and only 0.1% of those have Earth-like planets. And then a tiny fraction, maybe 0.001% of those Earth-like planets actually develop intelligent life.
Even with those tiny percentages.
You're still looking at potentially millions of intelligent civilizations in our galaxy alone. Just based on the numbers, statistically, the universe should be teeming. It should be loud.
Okay, so the numbers say lots of aliens.
Pretty much. And then there's the critical element of time. The universe is ancient. Staggeringly old, like 13.8 billion years old.
And Earth is, what, 4.5 billion? Relatively young.
Exactly. Our solar system formed much later. Life on Earth took roughly that 4.5 billion years to get from simple goo to, well, us. Technological intelligence.
Logically.
Logically, countless other planets could have gotten a head start, a huge head start.
Millions of years. Hundreds of millions.
Could be. Imagine a civilization that had even a million years head start on us. Think about our progress in just the last century. Radio, computers, space travel.
A million years. They could be unimaginable.
Unimaginable. They could easily spread across the galaxy. Maybe they'd build, giant energy extracting devices or send out numerous conquest ships, as one source puts it. Stuff we should see.
Massive engineering projects, signals everywhere.
Right. That kind of advanced, widespread activity, it should be incredibly visible, or at least detectable across enormous distances. You'd expect something.
But it does nothing.
But there's this profound observable silence. We haven't found any unequivocal radio and other transmissions. No solid evidence like probes, spacecraft, or astroengineering structures. Nothing definitive.
And that's the paradox.
That's the paradox. This glaring absence, this stark contradiction between what the numbers and logic scream should be happening and what we actually observe. Or rather, don't observe.
It really forces a reevaluation, doesn't it? All those childhood dreams of alien encounters suddenly feel, well, maybe naive.
It's a deep, unsettling problem. It makes us question everything we thought we knew about life, intelligence, and our own place in the cosmos.
So if the universe should be full, but we hear nothing, that's the core issue. Why are they so hard to find?
Okay, so to try and, get a handle on this cosmic silence, scientifically, one of the earliest and most famous attempts came just after Fermi's question, really, in 1960, from astronomer Frank Drake.
Ah, the Drake equation. I've heard of that. It looks very mathematical.
It does. He proposed this equation, N equals R FP, NaFL, phi FCL. It looks rigorous, like you could just plug in numbers and get an answer for N, the number of civilizations we could talk to.
Right. Simple.
Well, let's break down what those letters mean for you, because understanding them reveals both the equations, potential power, and its really profound limitations.
Okay, give me.
All right. R is the rate of star formation in our galaxy. How many new stars pop up each year? Astronomers are pretty good at estimating that now.
Okay, seems reasonable.
FP is the fraction of those stars that actually have planets. Thanks to missions like Kepler, we now know this number is likely quite high. Lots of stars have planets.
Good news for alien hunters.
Potentially. Ne is the average number of planets per star system that could support life. Think Goldilocks zone, not too hot, not too cold, maybe liquid water.
Still seems measurable eventually.
Getting trickier, though? Now comes FL. That's the fraction of those habitable planets where life actually arises. Abiogenesis.
Yeah.
How easy is it for non-life to become life?
Ah, that sounds like a big unknown.
Huge unknown. Then Phi, the fraction of those life-bearing planets where intelligent life evolves. Is getting smart inevitable once life starts, or is it a total fluke?
Another massive guess.
Yep. Then FC, the fraction of intelligent civilizations that are capable and willing to communicate across space. Do they build radio telescopes? Do they even want to talk?
Maybe they're shy. Or use something else entirely.
Exactly. And finally, the big one, L, the average lifespan of such a communicative civilization. How long do they stick around sending signals before they stop?
Before they go extinct.
Or just stop broadcasting?
Either way, they vanish from the communicable pool. You multiply all those factors together, and theoretically you get in a number of civilizations we could potentially chat with right now.
Okay, I see the problem. Some of those factors seem pretty solid, like star formation, planets. But others are just huge guesses.
Precisely, and that's where the subjectivity creeps in.
So when Drake first did this, what did he get?
Well, back in 1961, his estimates were, well, let's say, pretty optimistic, reflecting the excitement of the time, maybe. He ended up with N10.
10. So 10 civilizations ready to talk right now in our galaxy. That was the idea. And that number really fueled the early SETI efforts, the search for extraterrestrial intelligence. It gave people a solid, scientific-looking reason to believe the search could actually bear fruit.
But times have changed. What do estimates look like now?
Yeah. Fast forward to today, and you see estimates all over the map. Some using more modern, often more pessimistic values for those unknown factors. Mm-hmm. They yield a starkly different picture.
How different?
Well, some of the most reliable modern values, depending on who you ask and what assumptions they make, give you an N of something tiny, like 0.000225.
0.00. That's basically zero, isn't it?
Pretty much. It suggests no contactees right now, or that we are incredibly likely to be alone, at least in our little corner of the universe, based on those specific assumptions. Quite a tumble from Drake's initial 10.
Wow. From a potentially crowded galaxy to maybe just us.
Here's the crucial insight about the Drake equation, and maybe the uncomfortable truth about it. Despite its scientific structure, it ends up being less a calculator and more a mirror reflecting our own hopes, fears, and biases.
Because those middle factors, FL, Phi, FC, and especially L,
they're purely assumptions, as one source bluntly puts it. Educated guesses, sure, but heavily influenced by our one data point: Earth life and our own anxieties.
So different people plug in different numbers based on what they think is likely.
Exactly. It leads to wildly different interpretations. Take Carl Sagan, for example. He was famously optimistic about most factors being high, but he saw L, the lifespan, as the critical bottleneck.
The worry that civilizations destroy themselves.
Right. He used the equation powerfully, arguing that if L is short because civilizations tend to self-destruct, then we need to get our act together, avoid nuclear war, care for our planet to ensure our L is long enough to make contact or be found.
So the equation becomes a tool for advocacy almost.
In a way, yes, but that subjectivity, it really opens the door for criticism.
Like Michael Crichton, the Jurassic Park guy.
Yeah, he was famously scathing about it, called the Drake equation absolutely meaningless and has nothing to do with science. He basically said SETI is like religion, it cannot be disproven.
Ouch. That's harsh.
It is, but it highlights the frustration, right? Especially when you consider, as one source notes, about $50 million has been invested in SETI projects over the years, based in part on this kind of uncertain framework.
So a hopeful blueprint, but maybe a flawed one. Still, it frames the questions, doesn't it?
It absolutely frames the questions we need to answer. It tells us where the uncertainties lie, even if it can't give us the final number. And those uncertainties lead us directly to the possible explanations for the silence. Why are they so hard to find? Maybe the equation's factors are just incredibly small.
Okay, so let's dive into some of these explanations for the silence. One major category is what we call the Earth is special hypotheses, or the rare Earth argument.
The idea that we're basically a cosmic miracle.
Kind of, yeah. It proposes that the specific conditions needed for complex, multicellular life like us, capable of building telescopes and wondering about aliens, are incredibly rare, maybe unique in the galaxy.
So it's not that life itself is impossible elsewhere. Maybe simple microbes are common. Exactly. Maybe bacteria are everywhere, but getting from bacteria to, beings who can build civilizations, that might require a whole series of improbable coincidences, as the sources say.
A perfect storm of lucky breaks.
Precisely. And if that's true, then finding advanced civilizations is incredibly difficult because there just aren't many or any out there to find.
Okay, so what kind of coincidences are we talking about?
Well, it starts with our address. Our galactic location isn't random. Our solar system hangs out in a pretty stable orbit, kind of in the galactic suburbs.
Not downtown where all the action is.
Right. We're between the chaotic, radiation-filled spiral arms. This keeps us relatively safe from things like sterilizing supernova blasts for hundreds of millions of years at a stretch.
Which complex life needs, right? Long stretches of stability.
Absolutely. You can't keep hitting the reset button with massive extinction events if you want complex evolution. So our quiet galactic neighborhood might be crucial and perhaps rare.
What else makes Earth so special?
Our moon, our surprisingly enormous moon.
It is unusually big for a planet our size, isn't it?
Hugely. The leading theory is it formed from a really specific glancing collision with a Mars-sized object early on, a rare event in itself.
And what does the moon do for us, besides tides?
Critically, its gravity stabilizes Earth's axial tilt. It keeps us from wobbling too much.
Like Mars does. It wobbles quite a bit, I hear.
Exactly. Without the moon, Earth's tilt could swing wildly, leading to extreme rapid climate shifts. Imagine ice ages coming and going every few thousand years. That would likely halt complex evolution in its tracks.
Okay, so the moon keeps our climate relatively stable. Anything else?
Yeah, it likely helped keep Earth's core molten for longer through tidal forces. A molten core is vital for generating our magnetic field.
The shield that protects us from solar radiation.
Exactly.
Okay.
Without that magnetic shield, the surface would be blasted by harmful solar wind and cosmic rays. Life might be confined to deep underground or underwater, maybe never reaching complexity on the surface. So, no moon, maybe no us.
Wow. Galactic location of the moon. Feels like the list is getting long.
And it might go deeper, even into the fundamental physics of the universe. Dark energy, for instance.
The stuff making the universe expand faster. How does that affect aliens?
Well, some theories suggest that if there was too much dark energy early on, the universe might have expanded too quickly. Matter wouldn't have had enough time to clump together gravitationally.
So fewer stars, fewer planets, or maybe the right kinds of elements wouldn't form.
Potentially. It implies that even the basic cosmic recipe had to be just right, a delicate balance in the fundamental constants themselves.
Okay, so the conditions for Earth seem incredibly specific. This ties into the Great Filter idea, doesn't it?
It does, specifically the version where the Great Filter is behind us.
Meaning, we already passed some incredibly difficult step that almost nobody else gets through.
Exactly. Some wall or evolutionary bottleneck in our deep past. If that's true, it would explain the silence beautifully. We're one of the very, very few lottery winners. Advanced life is super rare because getting past that filter is almost impossible.
What could that filter have been?
It could be several things. Maybe the origin of life itself, abiogenesis. We still can't replicate it reliably in labs, turning non-living chemicals into self-replicating life. Maybe that's just astronomically improbable.
Or the jump to complex cells?
That's another candidate. The leap from simple prokaryotic cells, like bacteria, to complex eukaryotic cells with a nucleus and organelles that took billions of years on Earth. Maybe that's the bottleneck.
Or even becoming multicellular, getting cells to cooperate.
Also a possibility. These steps seem almost inevitable in hindsight, but maybe each one is incredibly difficult, a major hurdle that stops most potential life forms in their tracks. We just happen to clear all of them.
But is it all just luck? Or is there some predictability?
Well, that's a counterpoint. Some researchers, like Jennifer McCality mentioned in one source, suggest our existence might be more of an expected or predictable result, given Earth's specific geological and chemical history.
So less pure luck, more like following a complex but perhaps deterministic path.
Kind of. It suggests that if you get the right planetary conditions set up for long enough, maybe complex life is a likely outcome. But that still requires those initial conditions, the right star, the right planet, the right moon, the right location to be met in the first place.
So even if the process isn't pure luck, getting the venue might be incredibly rare.
Exactly. The combination of all these factors still paints a picture where complex, intelligent life could be exceedingly rare.
So what does this all mean? Maybe the universe isn't quiet because no one's out there at all, but because getting to the stage where you can be out there building radios, exploring space, is just astronomically difficult and rare.
That's the essence of the rare Earth hypothesis. A compelling, if maybe slightly sobering, explanation for why they're so hard to find. There just aren't many to look for. Hashtag 2.2, there's just different hypotheses beyond our perception. Okay, let's shift gears a bit. What if the problem isn't rarity, but the difference? What if alien life is out there, maybe even common, but it's just so fundamentally different from us that we're not recognizing it or we're looking in totally the wrong places?
Are human bias getting in the way? Anthropocentrism.
Exactly. Our thinking is so shaped by our own biology and environment. We tend to assume aliens need Earth-like planets, liquid water on the surface, maybe even look vaguely like us. But why should they?
So where else could they be?
Well, maybe they don't live on planets at all. What if they evolved beyond needing a home world? They could inhabit artificial environments.
Like giant space stations.
Yeah, maybe a whole fleet of giant space stations freely drifting in space, as one source suggests. Like our astronauts on the ISS, but on a civilization-wide scale. If they're not tied to a planet, maybe we're not scanning the right spots.
Okay, that's interesting. What about natural but non-Earth-like environments?
Think about subglacial oceans. We now suspect many icy moons in our own solar system. Jupiter's Europa, Saturn's Enceladus have vast oceans hidden under miles of ice.
Warms by geothermal heat, right? Not sunlight.
Exactly. Life there wouldn't care about starlight. It could thrive near hydrothermal vents, completely independent of the surface. Such a civilization might be entirely aquatic, potentially intelligent, but have zero interest or ability to look up at the stars or send radio signals.
They'd be completely hidden from us.
Completely hidden and possibly completely incurious about the outside universe. NASA's Europa Clipper mission is heading out to investigate Europa precisely because of this possibility. Finding life there would be revolutionary, showing us a completely different path life could take. And yeah, very hard to find from afar.
Okay, this next one sounds really sci-fi. Robotic life.
Yeah, here's where it gets really interesting, as you say. What if advanced civilizations inevitably transition away from biology? Maybe they upload their consciousness or develop sentient AI that replaces them.
So we're looking for squishy aliens, but they're actually machines.
Could be. Robotic life or machine intelligence might have totally different needs, appearances, habitats. They might not need atmospheres or water. Their civilization could be, I don't know, a planet-sized computer processing information or a swarm of nanobots re-engineering a star system.
How would we even recognize that as life or intelligence?
That's the problem. We might see some weird energy signature or unusual structure and just dismiss it as a strange natural phenomenon because it doesn't fit our definition of life or civilization.
Which leads to the idea that maybe we have seen them but didn't realize it.
Exactly. Our anthropocentric bias might be blinding us. One source puts it perfectly. Our confidence that we are familiar with the solar system is based on hundreds of thousands of images, none of which show anything resembling a bipedal ape. But who said aliens should look like that?
Good point. We're looking for something like us.
We might be missing civilizations that exist as energy patterns, or plasma clouds in nebulae, or collective consciousnesses spread across networks. Things so alien we lack the concepts to even describe them, let alone search for them.
And this applies to communication too, right? We're stuck on radio waves.
Mostly, yeah. SETI started with radio for good reasons, but maybe advanced civilizations moved on long ago. They might use highly focused lasers hard to intercept unless you're directly in the beam.
Or something even more exotic.
Perhaps neutrinos.
Yes?
Tiny, weakly interacting particles that pass through almost anything. Detecting a modulated neutrino signal would be incredibly difficult for us right now. Or maybe they use communication methods based on physics yet unknown to us. Quantum entanglement communication, gravitational waves. Things that sound like science fiction now might be galactic standard for them.
So if they're not using technologies we understand.
Then our searches are fundamentally limited. We might be listening for drums when they're communicating with light flashes or something we can't even imagine.
So this raises a really important question. Are we just limited by our own imagination, our own biology and technology?
It's a very real possibility. The universe is likely far stranger and more diverse than our Earth-centric viewpoint allows us to easily grasp. If they are fundamentally different, finding them becomes an exercise in expanding our own definitions, which is inherently hard. Hashtag 2.3, the they're gone or they're hiding hypotheses, the grim and the wary.
All right, this next set of ideas.
Yeah.
These are maybe the most unsettling, uncomfortable truths we have to confront. The possibility that they're not just different, but they're either gone or they're deliberately staying hidden.
Yeah, these ones hit closer to home, potentially.
Let's start with the really grim one, self-destruction. The idea that the great filter isn't behind us, but ahead of us.
This is perhaps the most sobering explanation for the silence. It suggests that maybe reaching a certain level of technological advancement inevitably leads to self-annihilation.
So civilizations rise, get powerful, and then destroy themselves.
That's the fear. Before they can spread across the stars or maintain communication for cosmic timescales, they wipe themselves out. And we can unfortunately see potential pathways for this in our own world.
Like what? Environmental catastrophe.
That's a big one. A civilization develops powerful industries, uses up resources, pollutes its environment, maybe creates too many undesirable chemicals and radiations that destroy the biosphere, making the planet uninhabitable for them. Technological progress outpaces wisdom, essentially.
Or just straight up war.
Nuclear war is the classic example. Discovering technologies like atomic bombs could be a common filter. Or maybe developing dangerous synthetic biology-engineered plagues created in labs that accidentally escape.
It sounds terrifyingly plausible.
It does. There's also the idea of societal collapse due to resource depletion. Or maybe, ironically, choosing sustainability could hinder them. If they limit energy use to protect their planet, maybe they never develop robust space travel.
So when a natural disaster hits asteroid, dying star, they're trapped.
Exactly. Nowhere to go. And then there are more exotic theoretical dangers, like maybe experiments with high-energy physics, like our Large Hadron Collider, accidentally creating a mini black hole that consumes the planet. Highly unlikely, but maybe possible at some future tech level.
So the implication here is this is true.
The implication for us is potentially inevitable doom, or at least a very, very challenging great filter that humanity still has to navigate in its future. Finding aliens is hard because they simply don't last long enough to become widespread or easily detectable.
Okay, moving from self-destruction.
Yeah.
What about hiding? The dark forest.
Right, the dark forest hypothesis. This draws heavily from science fiction, particularly Lou Sixon's work. It paints the universe not as empty, but as a dark, dangerous forest.
And every civilization, a hunter.
Or potential prey. In this scenario, every civilization knows other potentially hostile civilizations might exist. Resources are finite, the safest strategy for survival.
Stay absolutely silent. Don't reveal your location.
Exactly. Because any signal you send out is like shouting in the dark forest. It might attract predators. Maybe a more advanced civilization sees you as a future competitor or just an unknown variable and decides a preemptive strike is the logical move.
That's horrifying.
It is. The implication is that all too talkative civilizations have already been destroyed and those that remain sit quietly. The silence we observe isn't emptiness. It's the silence of the prudent, the hidden survivors. If they're intentionally hiding, finding them is basically impossible unless they want to be found.
Is there a less terrifying version of hiding?
Well, there's the zoo hypothesis. This one's a bit older, actually. It suggests advanced civilizations are aware of us, but they choose not to interfere.
Like we're in a cosmic nature preserve.
Kind of. They observe us, maybe study us, but they don't make contact, perhaps believing it would harm our natural development, or maybe they have some sort of prime directive against interference.
The Russian scientist Tsiolkovsky had a similar idea, right? Even before Fermi.
He did. He basically said advanced beings wouldn't treat us as equals any more than we'd go visit wolves or gorillas, except maybe to study them from a distance. Perfect animals of the heavens do not want to do the same destructive things with us. It implies a vast gulf in understanding and ethics. Again, they're hard to find because they choose not to be found by us.
Okay, let's talk about this newer idea, the universal limit on technological development, ULTD. What's the core concept here?
This is a fascinating hypothesis from Antonio Gelasfilo, proposed just recently in 2024. It suggests there might be a fundamental universal ceiling on how far any civilization's technology can actually advance.
A limit that's lower than we might think, like lower than needed for galactic colonization.
Exactly. Far below that level. The idea is that our technology is ultimately limited by our scientific knowledge. We invent tools like microscopes, telescopes, computers to extend our senses and processing power, but
Maybe the truly fundamental breakthroughs slow down.
that's the argument. Gelasfilo points out that many of the biggest revolutions in physics relativity, quantum mechanics, understanding the large-scale universe, happened nearly a century ago. To make the next giant leap, to answer the really deep questions.
You need what? Galaxy-sized experiments?
Maybe. Imagine needing a particle accelerator the size of the Milky Way or the energy output of a quasar just to test the next fundamental theory. That might simply be physically impossible for any civilization to achieve. An unbridgeable chasm, he calls it.
So progress hits a wall, not because of self-destruction, but because the universe itself imposes limits.
That's the idea. And if you can't make those scientific leaps, you can't develop the technologies needed for things like easy interstellar travel or communication. You plateau far below the starfaring level. And there's another layer to this, borrowing from Joseph Tainter's work on societal collapse.
Right, the idea that complexity itself becomes a burden.
Yeah. As societies get more complex, more specialized roles, more infrastructure, more bureaucracy, the energy and resources needed just to maintain that complexity keep increasing. Eventually, you hit diminishing returns.
It becomes too costly, too fragile.
Exactly. Tainter argued complex societies can become fragile and prone to collapse under their own weight, even without external threats or fundamental technological limits. So civilizations might just reach a certain level of complexity and then stagnate or collapse before they ever get close to interstellar capabilities. Another way they might vanish before we find them.
And one more physical limit, the super-Earth idea.
Right. This is more straightforward. We're finding lots of exoplanets called super-Earths, rocky planets, several times more massive than Earth.
Which means much stronger gravity.
Significantly stronger. So strong, potentially, that achieving escape velocity getting off the planet could be impossible, or at least prohibitively expensive in terms of energy.
So civilizations could arise on these massive planets but be permanently trapped?
Exactly. They could have thriving, complex societies, maybe even advanced technology, but they'd be gravitationally bound to their homeworld forever. Their sky might be full of stars, but they can never reach them. Another reason a potentially thriving civilization would be silent to our searches.
Wow. Okay, these theories, self-destruction, hiding, hitting limits, being trapped, they really force you to think about our own trajectory, don't they? And our own challenges right now.
Absolutely. They reflect our own fears and limitations back at us, making the silence feel very personal. And they all offer plausible, if sometimes grim, reasons why finding ET is proving so incredibly difficult. So, despite this profound silence, despite all these potentially grim explanations, humanity hasn't just shrugged and given up. We are still actively searching.
Right, the SETI effort. Where did that officially begin?
It really got its scientific legs in 1959. Two physicists, Giuseppe Cocconi and Philip Morrison, published a groundbreaking paper in the journal Nature.
What did they propose?
They advocated for a scientific search for radio signals from space. Not just waiting for UFOs, but actively listening with radio telescopes. And they suggested a specific frequency to target.
The famous hydrogen line. 21 centimeters.
Exactly. That's the natural frequency emitted by neutral hydrogen atoms, the most common element in the universe.
Mm.
The reason that any civilization advanced enough to do radio astronomy would know about this frequency. It's like a universal dial tone.
A natural meeting place on the cosmic radio dial.
Precisely. A natural, unique frequency standard, they called it. If you wanted to send a beacon signal to announce your presence across the galaxy, the hydrogen line would be a logical choice.
And did people start listening right away?
Pretty much immediately. In 1960, Frank Drake, him again, led the very first dedicated SETI experiment called Project OZMA.
Using a radio telescope, pointing it at nearby stars.
Yep, at the National Radio Astronomy Observatory in West Virginia. They targeted two nearby sun-like stars, Tau Ceti and Epsilon Eridani, both about 11 light-years away, close by cosmic standards.
And did they find anything? You mentioned a dramatic episode.
They did have one. Early on, the equipment picked up a strong pulsing signal coming from the direction of Epsilon Eridani. Apparently, the excitement was huge. They could even hear it on loudspeakers.
Wow. Was it?
It wasn't. The signal stopped, then reappeared the next day. This time, they were ready. They pointed the telescope slightly away from the star, and the signal kept going.
Ah, so not from the star.
Nope. Turned out to be terrestrial interference. Likely secret military radar tests or something similar. A false alarm, but imagine the adrenaline. It perfectly captured the hope and the potential frustration of the search right from the start.
It really highlights the challenge, doesn't it? Finding that one faint signal amidst all the cosmic noise and all our own terrestrial noise.
Immensely challenging. Frank Drake himself used the analogy of finding a needle in a cosmic haystack, but it's even harder than that.
Why harder?
Because it's not just a physical haystack, it's a multidimensional one. You need to search across 3 dimensions of space, where to point the telescope, time, when to listen, frequency, which radio channel, polarization, how the wave is oriented, modulation, how the signal carries info, and signal strength.
That's a lot of dimensions. 9, you said earlier.
A 9-dimensional search space. Early searches like OZMA barely scratched the surface, covering maybe 10, 17 of the total possibilities. We've gotten much better, maybe covering 10 now with modern tech.
Still a tiny fraction, though.
An incredibly tiny fraction, which is why critics popped up early on.
Like Sebastian von Horner.
Yeah, back in the 60s, he argued it was practically pseudoscientific to declare the universe silent based on our searches so far. He said our instruments were imperfect and unadapted for the test.
Because we're only looking in tiny slices of that haystack.
Exactly. Our search parameters for direction and frequency are so narrow, the probability of stumbling onto a signal, unless it's incredibly strong or deliberately aimed right at us, is negligible, as he put it. It's like trying to find a specific person in a global crowd by just randomly peeking through one keyhole at a time.
And even if the signals are there, we have trouble processing them.
That's another bottleneck. Seth Shostak from the SETI Institute points this out. Even if the sky is full of signals, we lack the simply enormous computing power needed to sift through all the data, filter out interference, and analyze every potential candidate signal in real time.
It's a big data problem on a cosmic scale.
Totally. We're getting better with projects like SETI at home distributing the load, but the challenge remains immense.
But there was one really tantalizing signal, wasn't there? The wow
Oh,
signal.
yes. The WOW signal. This is probably the most famous, most intriguing candidate signal ever detected. Gets you thinking, what might have been?
Tell us about it. What happened?
It was August 15th, 1977. The Ohio State University's Big Ear radio telescope, which was doing a SETI survey, detected this incredibly strong narrowband signal.
Narrowband, meaning not natural.
Exactly. Natural cosmic sources tend to emit radio waves across a broad range of frequencies. A narrowband signal is much more likely to be artificial, like a terrestrial radio station or potentially an alien transmitter.
And it was strong.
Very strong, and it lasted for the full 72 seconds that the telescope was pointed at that specific patch of sky as the Earth rotated. It matched almost perfectly what scientists expected an interstellar beacon signal to look like.
So what did they do?
Well, the astronomer monitoring the data, Jerry Eman, saw it on the computer printout later. It was so striking, so unusual compared to the background noise, that he famously circled it and wrote, "Wow," right there on the printout.
Hence the name. Did they ever find it again?
That's the mystery. They, and many others, have repeatedly scanned that same region of the sky near the constellation Sagittarius, but the signal has never, ever been detected again.
Gone.
Vanished. It remains completely unexplained. Maybe it was a transient alien signal, maybe some unknown, rare natural phenomenon, maybe incredibly unusual terrestrial interference that just happened to mimic an alien signal perfectly. We just don't know.
Wow. Wow. Signal is like this cosmic whisper in the dark, isn't it? A brief hint that just left us with more questions. A perfect example of how hard this search really is.
Exactly. A tantalizing, frustrating, and ultimately unresolved mystery. So the search didn't just stay stuck on radio waves, especially after the initial lack of success. Scientists started thinking, okay, maybe radio isn't the only way or even the best way for advanced civilizations to communicate.
Looking beyond the 21-centimeter line.
Yeah, and beyond radio altogether. The idea of optical SETI, or OSETI, searching for laser signals, gained traction. Nobel laureate Charles Townes, one of the inventors of the laser, proposed this back in 1961.
Lasers. Why lasers?
Well, lasers have advantages. You can concentrate energy into a very tight directional beam. This means you could send powerful, information-rich pulses over interstellar distances, maybe more efficiently than a broad radio broadcast.
But harder to detect unless you're right in the beam.
Exactly. It's like trying to see a spotlight from the side versus looking right into it. So OSETI searches look for brief, powerful flashes of monochromatic light from stars. They might offer better detection ranges for nearby stars, say within 20-30 light years.
So expanding the type of signal we're looking for, what about looking for signs of alien activity, not just signals?
Right. That brings us to ideas like Freeman Dyson's. He famously popularized the concept of Dyson spheres.
These massive structures built around stars.
Yeah, hypothetical megastructures that a very advanced civilization might build to capture nearly all of their star's energy output. Imagine the power.
What would that look like from Earth?
Well, the sphere would block the star's visible light, but it would have to radiate waste heat, so it would glow brightly in the infrared spectrum, a very distinctive signature.
And have we found any?
Astronomers have searched for these characteristic infrared signatures, looking for stars that are dim optically but bright in infrared. There have been a few intriguing candidates, like Tabby's star, but so far, no confirmed Dyson spheres. The silence extends to megastructures, too, it seems.
Dyson also talked about self-replicating probes, didn't he?
He did. Von Neumann probes, sometimes called. The idea is you send out one probe to another star system. It uses local resources to build copies of itself, and those copies then travel to other stars, and so on.
Exponential expansion.
Exactly. Theoretically, such probes could explore or even colonize an entire galaxy in just a few million years, which is short on cosmic timescales. If they exist, they should be everywhere by now. But again, we don't see any evidence.
Okay, so we're looking for signals, looking for structures. How else can we categorize potential aliens? I remember the Kardashev scale.
Ah, yes. Nikolai Kardashev, the Soviet astrophysicist, he proposed classifying civilizations based on their energy consumption, which gives us a framework for thinking about what kind of signals or evidence different levels of advancement might produce.
Type I, Type 2, Type 3.
That's right. Type I civilizations can harness all the energy available on their home planet. We're arguably approaching this, maybe Type 0.7 right now. Type 2 can harness all the energy of their host star. That's where a Dyson sphere comes in. This is a huge leap in capability. Type 3 can harness the energy output of an entire galaxy. We're talking galactic-scale engineering, manipulating billions of stars, maybe tapping into the supermassive black hole at the galactic center, almost godlike power.
And Kardashev thought we should look for the really advanced ones.
His argument was that Type 2 and especially Type 3 civilizations would be so powerful, their activities so large-scale, that they should be detectable even across intergalactic distances. Their energy use would make them stand out. If they exist, they should be obvious.
But again, we don't see them.
The silence remains, which either means they don't exist or maybe our assumptions about how they'd use energy are wrong.
What about the search efforts today? Is it still just big telescopes?
It's evolved a lot. Public participation is huge now, thanks to projects like SETI at home. Millions of people donate their computers' idle processing time to analyze data from telescopes like Arecibo used to, or Green Bank now. It creates this massive distributed supercomputer.
Democratizing the search.
Totally. And there are dedicated next-generation facilities being built or planned, like the Allen Telescope Array in California, specifically designed for SETI searches, and the huge International Square Kilometer Array, SKA project.
Which will be much more sensitive.
Hundreds of times more sensitive than current instruments. They'll be able to scan much larger areas of the sky much faster across a wider range of frequencies. If there are signals out there, these new telescopes significantly increase our chances of finding them.
So far, we've mostly talked about listening, SETI, What about shouting? Mediati,
Right, meaty messaging, extraterrestrial intelligence. This is the active approach. Sending messages out into space, hoping someone might detect them.
like the Arecibo message. That picture we beamed out in 1974.
That's the most famous example. A simple pictographic message sent towards the globular cluster M13. There have been others too, like messages sent from the Evpatoria radar in Crimea, sometimes carrying things like music or art. Someone even transmitted the Beatles across the universe towards Polaris.
Is that wise? The whole dark forest idea.
That's the debate. It definitely raises meaty phobia concerns for some scientists. Stephen Hawking, for instance, was famously cautious about advertising our presence. Why shout into the jungle if you don't know what's listening?
But others argue we're already noisy.
Yeah, the counter-argument is that Earth has been leaking radio and TV signals unintentionally for over a century now. Our planet is already lit up like a Christmas tree at radio frequencies. So maybe deliberate messages don't significantly increase the risk, if any exists. It's an ongoing ethical and strategic debate.
Okay, looking really far ahead, are people thinking about communication beyond light or radio?
Absolutely. This pushes the boundaries of physics, but yes. Scientists theorize about using gravitational waves, ripples in spacetime itself to communicate. Or maybe using neutrinos, those ghost-like particles.
Would that even be possible, detecting modulated neutrinos?
Extremely difficult with our current tech, but maybe not impossible for a super advanced civilization. Kardashev even speculated about using wormholes, theoretical tunnels through spacetime, for near instantaneous interstellar communication or travel, bypassing the light speed limit entirely.
Okay, now we're deep into science fiction territory.
Pretty much, but it shows the breadth of thinking. If civilizations are using methods like these, they could be communicating all around us, and we'd be completely oblivious. It underscores just how vast our ignorance might be, and how truly different and hard to find advanced intelligence could be. So wrestling with the Fermi Paradox, exploring all these potential explanations for the silence, it inevitably forces us to look inward, to reflect on fundamental questions about life itself. Where do we come from? How likely is life, really?
It puts our own existence into sharp relief, doesn't it?
It really does. There's this long-standing philosophical split among biologists, kind of two opposing camps.
Like who?
Well, on one side, you had figures like the biologist Christian de Duve. He argued for what he called a cosmic imperative, the idea that life isn't a fluke but an almost inevitable outcome if the physical and chemical conditions are right.
So life should be common, according to him, at least simple life.
Yeah, basically, wherever the ingredients and environment allow, life will likely pop up. It's almost written into the laws of physics and chemistry.
Okay, who's on the other side?
On the other side, you had scientists like Francis Crick, co-discoverer of DNA's structure. He was much more pessimistic. He viewed the origin of life as a highly improbable event.
Meaning Earth life was just an incredibly lucky accident.
Pretty much a chemical fluke that happened here, but might be extraordinarily rare elsewhere. So under this view, we might genuinely be alone, or almost alone, because the initial spark of life itself is the great filter.
The Fermi Paradox kind of forces you to pick a side, or at least lean one way.
It does, or it makes you question both extremes. And what's fascinating now is that our growing knowledge is challenging these fixed positions.
How so? Finding all these exoplanets, learning more about biology.
Exactly. We now know potentially habitable planets are common, and we're learning more about the complex pathways that could lead to life. This is leading to newer theories, like the work of Jennifer McCalady we mentioned earlier.
The idea that life might be a more expected result of planetary evolution.
Right. Not necessarily easy or guaranteed, but perhaps a more predictable outcome if you have the right sustained conditions, the right geology, the right chemistry, the right energy sources over billions of years. It suggests maybe life isn't a miraculous fluke or a simple inevitability, but a complex emergent property of certain types of planetary systems.
So, maybe simple life is common, but the path to intelligent communicative life is still fraught with peril and low probabilities.
That could be. It still leaves plenty of room for filters later on, but it shifts the perspective slightly, suggesting the universe might be more predisposed to life than Crick thought, even if it's not the cosmic imperative de Duve envisioned. Finding life, even microbial life, on Mars or Europa would dramatically change this whole conversation.
Absolutely. So this whole deep dive, it's not just about finding aliens out there.
Not at all.
It's fundamentally about understanding ourselves. Looking in that cosmic mirror, reflecting on our own origins, our own uniqueness, or maybe our own commonality.
Precisely. The act of asking, where is everybody, inevitably leads back to who are we and how special or how typical is our story. It's a deeply philosophical question wrapped in a scientific puzzle. Hashtag 4.2 Humanity's Future reflected in the paradox. And that brings us to perhaps the most direct and potentially uncomfortable implication of the Fermi Paradox for humanity right now.
The possibility that the hardest part is still to come. The great filter ahead.
Exactly. If the silence means that most advanced civilizations don't make it long-term, whether through self-destruction, societal collapse, or hitting some universal limit on technological development, then that serves as a profound warning for us.
Our own future might be reflected in that silence.
It's a chilling thought. It suggests that reaching our current level of technology isn't the finish line. It might just be entering the most dangerous phase. Advanced civilizations might be inherently unstable, fragile things. The silence isn't just about the past of other potential civilizations. It could be a forecast of our own future if we're not careful. It's perhaps the starkest explanation for why aliens are hard to find. They blink out of existence relatively quickly on cosmic timescales.
Which loops back to Carl Sagan's point about the Drake equation, doesn't it? That L, the lifespan, is the crucial factor we need to worry about.
Absolutely. From Sagan's perspective, the paradox isn't just a puzzle. It's an urgent call to action. It compels us to confront the existential risks we face: climate change, nuclear war, pandemics, resource depletion, the unforeseen consequences of powerful new technologies like AI or genetic engineering.
We need to increase our own L.
We need to actively work to ensure our civilization is sustainable, resilient, and wise enough to navigate the challenges ahead. Our ability to overcome the potential great filter isn't guaranteed. It depends on the choices we make now. The silence becomes this cosmic background noise reminding us of the stakes.
So is it all doom and gloom? Does the paradox offer any hope?
I think it does, in a way. As one source puts it, despite the silence, the paradox still makes the hypothesis of extraterrestrial life at least possible, if not probable. It keeps the question open.
And the fact that we are here, asking these questions.
That in itself is remarkable, isn't it? Our very ability to contemplate the universe, to search for others, to grapple with these profound questions about existence. That hints at our own unique journey, regardless of whether anyone else is out there. Maybe the silence is simply highlighting how precious and extraordinary our own consciousness is.
A reason to cherish what we have, perhaps.
Definitely. The quest to
So, as we wrap up this deep dive, it's pretty clear the Fermi Paradox is far from solved, isn't it?
Not even close. It remains one of the biggest, most tantalizing questions out there.
It's this profound puzzle, really an uncomfortable truth maybe, that scientists, philosophers, and honestly, all of us continue to grapple with. We've explored this mosaic of possibilities today.
Yeah, from the incredibly specific conditions needed for a rare Earth.
To the chilling thought of civilizations destroying themselves or hiding in a dark forest.
Or maybe hitting fundamental limits or just being so fundamentally different that we wouldn't even recognize them.
Each theory pushes our understanding, challenges our assumptions, and offers a compelling reason why finding evidence of extraterrestrial intelligence remains so incredibly difficult.
Absolutely. And that's why the silence of the cosmos ultimately isn't just an absence. It's more like a mirror.
A mirror reflecting back on us.
Yeah. It forces us to confront not only the sheer vastness of space and time, but also the profound limits and maybe the incredible potential of our own existence.
So maybe the most uncomfortable truth isn't really about the aliens, or lack thereof.
Perhaps not entirely. Perhaps the most uncomfortable truth is that the answer to Fermi's simple question, where is everybody, might ultimately tell us more about our own future trajectory, our own challenges and choices, than it does about the universe's populated past.
And what we choose to do with that reflection.
Yeah.
That's the real question.
That's entirely up to us.
Keep looking up, keep asking questions, and keep diving deep with us.